Okay guys, it's already 6:35. We are like almost 10 people. So 3, 4, 7. 7 of you are joined. One is already on leave. He already stated in the group that he will not join, and it's just Rahul. Okay, one more person is left. Okay, we can start, I guess. So, welcome everyone in this session. So, here in this session, we will try to understand the distributed file system and how the distributed compute works. Okay, but before that, I wanted to go through the Python assignment that I have shared some time before, and I expect you guys might have done and put some efforts to solve it. So let me share my screen. We will go through the assignment, and it will be really great if it is more interactive. Like we will go through the assignment question one by one, and any of you can unmute your mic and can tell me how you approached it. Okay. Okay. So now you might be able to see my screen. This one is the Python assignment. Okay. So talking about the first question, find the element in the middle of the array. Had anyone tried that? Mm-hmm. Mm-hmm. Okay. It's totally correct. Yeah, it's totally correct. Like anyway, we had to find the middle of the array. So we had to get the middle index. And to get the middle index, we had the length of the array divided by 2. Straightforward, simple. Okay, let's go to second one. Sort an array in ascending order. Anyone tried? Mm-hmm. Okay. Basically, I was expecting like you will be writing some small code to sort it instead of just using the sort function. But it's totally fine. Like in the while working in the jobs, we, we will not sit and write the sort things. We will use directly the sort functions that are already provided by the Python library. So if I talk of sorting an array from a very naive sense, um, let me just open okay. So let's say I had some array 2, 3, 2, 2, 3, 2, 6, 1. Okay. So the sorted version of this array would be 1, 2, 2, 3, 6, right? So how to achieve from this state to this state? So we had to think in terms of logics. Okay. Now we know the concept of swapping two elements. So just the most naive thinking that will come to my mind will be like, what if I swap all the small elements to the initial places, right? But if I swap it, then my current element will go at the last, or whatever the position for my smallest element. So what I can do, I can iterate it. Instead doing like this, what I can do, I can select the element one by one, and can compare it with the individual element. Okay. And where if my current element is small, if my current element is is greater than this, if my current element is smaller than this element, the next element, then that means it is perfect, it is perfectly fine. But if it is not, let's say we arrived at this position, then what we will swap it, we will swap its positions. So similarly, we can do it for this element, we can do it for this element, we can do it for this element, and eventually we will end up having a sorted array, right? Like if this might be confusing when I say it from an overall picture. Let's say I had two counters, I and j. Okay, j I will set it on the runtime. So what I am doing is, while I is less than my length of this array, and while my j is, so I will set j equals to I plus 1, because every time for this particular element I wanted to swap it from the next, I will search the comparison for this element for the rest of the one. Then I will search the comparison for this element for the rest of the element. So if my I is 1, so j should start from I plus 1 every time. And then I can say, since it is starting from here, while my j is less than my length of the array, if that is the case, what I will be doing, I will be checking if my current element is greater than the element at I was searching here. If my current element is greater than the element I am searching here, then I had to swap that. How I can swap? Temp equals to array of I, the very traditional way that we had discussed. Now I can update the value of I because I have already saved it, and then I will update the value of j with my temp. It's swapped. Cool. And every time we go through it, we will increase the j to 1, because otherwise it will be an infinite loop, and I will increase I by 1 to make it a finite loop outside. So if I keep on doing this, I will have the sorted array. Like if I illustrate how this will work, how this particular code will work. So if you see, when my I is 0, j is 1, comparison will not work, because 3 is already, is 2 greater than 3? No. 2 greater than 2? No. 2 greater than 6? No. 2 greater than 1? Yes. Swap them. 1 3 1 3 2 6 2. Now my I will move to this place, and j will start from here. So is 3 greater than 2? Swap it. 2 3 6 2. Now 2. So is 2 greater than 6? No. Is 2 greater than 2? No. Now I will move to this place, and j will start from here. Is 3 greater than 6? No. 3 greater than 2? Yes. So it will swap. 1 2 2 6 3. Now again I will move to 6, and j will be 3. Is 6 greater than 3? Swap. 1 2 2 3 6. We arrived at the final destination. So this particular algorithm that I talked about, it is known as bubble sort. Okay, so like, are you clear with the logic? Like, how I was just explaining a two pointer concept here by means of explaining the sorting algorithm. So this two pointer, you can use two pointers wherever you had to do the comparison on two sides of the array. Like, um, you wanted to run certain algorithm which wants to compare multiple elements with a single element, or like, based on the use case, you will come to know. So is this looks clear to you? Okay, let me just also run it. So if I use the sort array function and give this similar array, since I haven't written a return function, it will not return me anything. So I have to say say it like this, then I can print this array. Okay, so I have set it the array, this arr equals to this, and now I pass it to the sort function. It sorted this array, and then I'm printing this array. Right, it works as we expected. All right, so you guys are clear about this, right? How the two pointer thing, um, how I am using I and j to point specific elements to the array, and how I am making the comparison to make my logic works. Okay, then this one, the third question: find if a string is a palindrome or not. Okay, uh, so many of you, those of you who doesn't know what a palindrome is a string. If you uh, read it forward, or you read it from backward, it sounds same, like radar, radar. So if you read it from backward as well, radar, so it's a palindrome, level, level. Okay, so given a string, we had to identify whether the string given a string is a palindrome or not. So anyone tried doing that? Hmm. Check the max. Basically, string is also an array of characters only. Like, if I show it to you, so let's say I say a string race car. Okay, so this is an array of character. Like, if I wanted to access the zeroth element, so zeroth element is r, first element is a, zeroth element is r, a. It's like that. Mm-hmm. So you wanted to say, like I can select a j, let's say, when you are saying length of s minus 1 to be an index. Okay. Mm-hmm. This one append to this one. Okay. Uh, I didn't get it actually, but you can talk in the same way. Like let's say we talked about this one, reverse array using swap, right? So we talk of the left one and the right one. So we can go with a similar way. Set L, set the R. Wherever my L is equals to R, keep on continuing. Increase the L, decrease the R. And if you keep on getting the same values and your L is greater than the R, then it means it's a palindrome. And if it doesn't match, then it's not. Yeah, makes sense. Do you need me to write the code quickly, or is it fine? Then also we can do. We can reverse this string and we can check whether the contents of the both of the string are equal or not. So, I can see only Anil is talking. Rest of the class like Somya, mm, Nived, Khalil. Are you? Are we on the same page? Akhil. If you guys talk, then it would be really better. Okay, thanks. Okay, so the fourth question is given an array where we had the natural numbers with the missing element. So, what we mean by natural number? Natural number could be a continuous series of number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 up to infinity. Okay, so from this natural numbers, there is an element missing. So we had to identify which element is missing. So 1, 2, 3, 4, 6, 7, 5 is missing, right? So we had the answer to this missing element for this particular array would be 5. So how we can do that? Anyone apart from Anil who might have done? Or if let's say if you haven't done it, but do you have any idea of uh, how you will approach this? Okay, I think let's discuss. Let me give you one more day. Maybe you can give a try to rest of the four questions, and then we can discuss it in the next class. Yeah, Anil, but seems like rest of the classes have not even touched it. Uh, like it's it's no brainer for me to discuss all, but it's important to keep the class on same page. Okay then, we will discuss the rest of the four questions tomorrow. So I want uh, in the last session, Rahul might have gave you an overview about the Hadoop architecture and what the Hive is and what the Hadoop is used for, right? So I just wanted to extend on top of it exactly how Hadoop and like inside Hadoop, Hadoop is what? It's a framework. It's it provides you multiple components like HDFS, Hive, MapReduce. So all these components sums up for different things. Let me draw a few things. Maybe that would be more better for the illustration purpose. Okay. So when we talk about Hadoop, so Hadoop is a overall framework. Okay. So this is Hadoop. Now inside Hadoop, we had so when we have data, we wanted to do three things. We wanted to store it, we wanted to store it, we wanted to compute the data, we wanted to query the data or search the data. Okay, three basic steps. So to for storage purpose, it provides HDFS. HDFS is Hadoop Distributed File System. We will talk about it. For compute, it provides MapReduce. Mind my writing, okay. So for search, it provides Hive. Okay, so let's talk about HDFS first. So when we talk about big data, so we had to store the big data somewhere. Since the data is big, big could be any number. Like if I am having a 1 GB a machine having 1 GB of hard disk, big data could be a 2 GB, right? So basically a data that I cannot store on a single disk. That is the size of the data. So let's say you have 1 TB of data, okay, and you had you had some of the disks, okay. Let's say this is machine 1, this is machine 2, and this one is machine 3. So let's talk about 3 machines, or just for sake of simplicity of the calculations, let's talk about 4 machines. So when a file system is distributed, instead of keeping a single file onto a single machine, it splits the file. Okay, so let's say a 1 TB file we have. So a 1 TB file will split it up, since we are storing it in 4 machines. So it could be 250 GB, 250 GB each, right? Now so this thing is straightforward. We are splitting the data and storing it on the machines, but how exactly it could be? Now we had talked about tables, right? Similar to SQL, or you can think of an Excel file. A table have columns, rows. So while splitting, let's say it carry 1,000 rows. So 250 are stored here, and 250 are stored in machine 4. Now what happens? So this HDFS is supposed to be said as highly available and fault tolerant. Okay, let me highly available and fault tolerant. So what do we mean by highly available and fault tolerant? A system is highly available when it is having no downtime. Okay, and fault tolerant if a system breaks, then it is able to recover itself. Okay, let's see both of these via an example. Let's say I had some data. I had some data, some 250 GB of data on machine 1, similar to other machines as well. And somehow my machine 1 crashes. Okay, my machine 1 crashed. So what happened to this 250 GB of data? I wouldn't be able to recover my whole file. I am left with only 750, 250 gone. So for that purpose, it do replicates the data onto multiple machines. So generally, by default, it has a replication factor of 3. So each data block is replicated 3 times. So now, if I talk about this 250 GB, so let me mark it as first part of this 250 GB. So this first part of this 250 GB is stored here as well and here as well. The second part of 250 GB is stored here, let's say here, as well as here, something like this. So you can see the first part of this 1 TB is stored on three separate machines instead of single machine. Now if my first machine crash, then I can still recover the whole file because I had the blocks available in the another machine. Okay, makes sense. So this way it is fault tolerant. My machine 1 goes down, it doesn't affect my system. I am running this on thousands of machine. Any of my machine uh, m- during my runtime, any of my machine can go down. I will add more machines, and once I will add up another machine. Like this, my old machine is down, so I respun up a new machine. So based on the replication factor, it will again create the block of this. Now I again have the replication factor 3 and my data is still serving. I'm able to read my data. So this is how it is fault tolerant. And since I am always able to retrieve my data no matter what, that means my system is highly available. Okay, got the 2 points, how it is highly available and fault tolerant. Okay, now coming to how this particular data is retrieved. Okay, uh, let me talk about the speeds as well. Now when you're running on your own hardware, let's say you are attending this class on some system, right? So in the system you had one hard disk, so it have some definite read and write speeds. So let's say you are using some hard disk based laptop where it provides some read speed of some 100 MB per second and reads and some, let's say, 50 MB per seconds of write. So this is the hard disk limitations. It cannot go up beyond that. So if I have a very huge data, like let's say 1 TB of data, how much time will it take to read this 100 with this particular speed? It will take a lot of time. And I'm just talking about 1 terabyte. Big data could be of any size, right? So this particular HDFS gives me an added advantage since I am able to retrieve the data from multiple machines, okay, and it is split on in the form of blocks on multiple machine. So instead of reading the 1 terabyte from a single machine, what I can do, I can, if I wanted to read this first part, I can read it from any of the machines. So let's say I'm reading it with 100 MB per second for the first part, and even the second part of this file, I'm reading at 100 MB per second. So cumulative speed is a lot. I will get the parallelism benefit, right? Because I am reading from multiple machines. I'm reading from multiple hardware. So this HDFS will help me to speed reads and write by parallelism. So parallelism is inherent in the all the Hadoop system of the Hadoop system design. Okay. Now let's talk about how a data file is stored and how we are able to retrieve that file. Okay. We talked about the benefits. We talked about how the file is splitted. But for to read the splitted file, we need to know which file stores at where, right? So let's say, so for HDFS, there are two components. Okay, Rahul might have talked about it. So for a single machine, there will be one name node and we had data node. Okay. So what this name node and data node are? So data node is simple by name itself. It stores data. We stored this block of 250, the first block of 250 GB, second block of 250 GB in different machine M1 and M2. So these are the these are the data nodes. Okay, but we need some place where we store that this particular block is stored in this machine, some sort of mapping. Okay, let's say this I had some identifier, like we call it a primary key in a SQL. So let's say I had the identifier one underscore 1 TB file. Okay, so this is one identifier I was thinking for. So it will have a mapping, like the first part is stored in machine 1, the second part is stored in machine 2, third part is stored in third machine, and the first part is also stored in machine 3, like that. Okay, so when I as a user will ask this name node where my I wanted to read this data, so this will point me, like this is here is my block, go to this machine 1 and fetch this block, go to machine 2, fetch this block, go to this machine and fetch this block. So I will this will redirect me to the data nodes and will help me and create the requests on my behalf, and I will be able to fetch the data. Up until now, does all these things make sense to you? Yes, no. I was just giving one example. Let's say you had a 1 terabyte of file. So it is since we had four machines, so I split it into 250 GB each. So I was saying, let's say you had, since you are splitting it into four parts. So the first part of this 250 GB is stored in machine one. Second part may be stored in second machine, like this. Just try. Mm-hmm. Yep. So once every time it stores the whenever it stores a block on certain machine, it stores with a replication. What does replication mean? I will replicate that block on the specified number of machine. So the default replication is 3. Okay, so while persisting the first block of this 250 GB, I will be storing it. The first part is stored in machine 1 as well, machine 3 and machine 4. Okay, so if 1 is down, I still have 3 and 4. So this is how it is fault tolerant. No matter if my machine failed, any of my machine failed, then I had other machines standby to serve the requests. Right. So if you are storing 1 terabyte of data in HDFS, that means you are since the because of the replication, you will be storing it 3 GB, 3 terabyte of data, because you are replicating it 3 times. Okay. So this is the concept of name node and data node. Name node have the mappings where your data is stored. Data node, it stores the data. Okay, straightforward. Okay, now so this is a simple way. Now let's say what happens if my name node is crashed. Okay, like I had the backup of the data node, because each file is replicated on multiple nodes, right? Each file is replicated 3 times. So if my data node crash, then it doesn't affect me because I had the data available on the rest of the machines. But what if my name node crash? Because name node is a single, now the single point of failure. So if name node crash, what it do is, to make it fault tolerant, it maintains two name nodes. This is name node 1 and this is name node 2, and there could be multiple as well. Okay, so anyway, a single name node will be serving all the requests. Okay, and the secondary name node will keep on copying the mappings. So if since it is just a backup node, and it this one keeps on copying the primary one. All the things were served from the primary. Secondary one will keep on copying from the primary. If my primary is down, if my primary go down, it crashed, then I already had all the copy in the secondary one, and it will start serving as the name node, and the system will keep on working. Okay, so this way the distributed file system works. It carries all the mappings, it carries all the data, and it doesn't matter if one machine crashed or another machine crashed. It is fault tolerant in a way. And this is how the data is stored in an HDFS, and what a distributed file system is. So I'm just talking about the distributed file system. It's not specifically for Hadoop only. This concepts applies same on Google distributed file system, or uh, any of the distributed file system that exists. Okay. So now we have talked about how we store the data in a distributed fashion. Now, how to compute this data? Okay, let's say like if everybody is fine with the HDFS, can I move to compute? Just if anyone can unmute and say yes, we are fine. Or if any questions, then ask right now. I'm already trying to be very simplistic in the sense how I'm teaching with all the machines without using any technical jargons. Okay. Uh, so still, if you're having any trouble understanding, please do unmute. Let me know. Then only I will be able to clear, because sometimes there exists some gap. Since you guys are from non-technical background, non-CSE background, basically. Okay. So we had done the storage part. Now let's talk about compute. How to compute a data that is stored in a distributed fashion. Let's come back to our four machines. Machine 1, 2, 3, and 4. And we had the data available in all four of the machines. So this time I will go a little bit deeper into the records as well. So let's say when talking about the 250 GB of data, okay, I am listing out few records. Let's say I had a player table that we discussed in SQL, where I had a player ID and the player name. Okay, and the player date of birth. So player ID, let's say 1, it is Sachin, and the date of birth is like 0 August 97, like uh, August 97. Or another record like Ashish, February 91. Something similar records are here as well. ABC 01 92. Some records here and some records here. Okay. And so this I just gave a small illustration. It have the data size of 250 GB, so it might have like 50 million records. Okay. So now our objective is, let's say we wanted to compute the age of my player. To compute the age of my player, I know a very simple step. What I can do, I will since I already have the date of birth, I will subtract the number of years from the current years minus the year he's born, and that will be the player's age. That's how we calculate age, right? But we had to perform this same compute on the files that is stored in distributed fashion, and we had to compute. Since it's a big data, we cannot compute it on a single machine. We had to compute it in a distributed way. So how it works is, it works in this way of map reduce. Okay, where the map refers all the things that we can do parallelly. Okay, and the reduce refers to all the things which require aggregation. Let me explain you. When I talk of map means things that we can do parallelly. Hmm? To do things parallelly, to do things parallelly, uh, what I mean is, like right now, yeah, yeah, right now, we had the age. Okay, to compute the age, we just had to mind what we had to do. We had to reduce the current year from the date of birth year, right? This will be my age. Can I do this computation independently on each all of the records? By independently, I mean like 1, 2, 3, 4, 5. Let's say this is an array, okay, and I wanted to add 1 in all of the elements. So one way of doing it is, I I start from I equals to 0, and while my I is less than the length of my array, I will iterate through this array, and I will increase this value by 1 and increase I, right? This is one way. So in this way, what I am doing is, I am keep on incrementing the I and adding 1 to all of the elements. Another way is, since adding 1 or the another element doesn't affect the third element. If I add 1 parallelly in all of these array indexes, then still my result will be same, right? So this adding the 1 can be done parallelly. I don't have the dependency of the first and the last element to do so. I can apply this function to add 1 independently on all data points. So all the things that can be done parallelly is done in is what we call map side. So can we calculate the age independently of all the records? Can anyone of you answer? Yes, we can calculate it parallelly, right? Because it's I had separate DOB of all the records, and current year will gonna stay same. So I can compute this age function to on all the records parallelly. So what it will do is, it will read the data. So the data is stored in machine 1. So it will take it will read the data in itself and compute this this particular function on all the records parallelly. the second machine will work parallelly, the third machine will work parallelly, the fourth machine or n number of machine will operate parallelly and will perform the compute, and you will be able to calculate the age in a matter of seconds, even for 2 TB or 3 TB of data, or any size, because it's horizontally scalable. Add more machines, you will be able to compute more, you will be able to store more, right? Now let me talk about the reduce part of it. So let's say again I had one array, okay, and what I wanted to achieve is I wanted to take the sum of all the elements. Hmm? To take the sum of all the elements, would I be able to achieve it independently for all the records? I cannot, because the sum will depend on all the records. 1, 2, 3, 4, 5. 1 plus 2 plus 3 plus 4 plus 5. That is my answer. So, wherever I require the items to be aggregated, because only when we want the aggregation, like sum, average, or percentile, or like could be any aggregation, any sort of aggregation, there we cannot compute it parallelly. We need to club the records together. So for that, there will come the reduce phase. Now see, every time whenever you are doing aggregation reduce the number of records, like you are trying to count. So if you count all these values, if you count all these values, so the answer will be 5. It reduces the number of records, so that's why the name is reduce as well. Okay, you can remember it from this way. So how the reduce work? So let's say you want let's think from a query perspective. Okay, um, let's say we have a data set, okay, which is like my restaurant ID, and I had the food item, food name, and the price. Okay, and I had some values, like if my restaurant ID is ABC, I have a burger, I had some price like $10. Another from, like it could be um, nuggets, $5, something like that. And we have another more restaurants, we had more foods, we had more price. What we wanted to do is we wanted to run a simple SQL query where we are selecting my restaurant ID, and I wanted the sum of the price based on my restaurant ID. We have two more people, right? Seven joined. Let's wait for 1 minute. They will join. Otherwise, we will continue. So you guys are clear by whatever concept I'm telling you, right? Okay, I think those guys are not joining back. Let me continue. So by this thing, I wanted to illustrate how a distributed compute work by running a SQL query on a table, which we will store in a distributed fashion. Okay. Let's say we are running a select restaurant ID, and based on the restaurant ID, grouping on the restaurant ID, I am trying to sum up the price from this table group by on restaurant ID. Okay. So here we are performing an aggregation. To perform an aggregation, let's say this particular data set might have distributed on these three machines, and it stores like this ABC, this whatever the name is, burger or anything, this 10 ABC, anything 20 ABC, anything 15, and some CDH 20, CDH 60. Okay, so we wanted the sum of all the prices to we since this sum is an aggregation, we cannot perform on the map side because we need to aggregate the records. One record is dependent on another to perform the computation, so this will be done in reduce side. But to perform the reduce side as well, how we need, like if you think from a very basic perspective, we need to sum up all the prices where I have the content, like the restaurant ID as ABC, or say where I'll be having similar restaurant ID. Hmm? So to do so, I first need all the records which are having same restaurant ID in same machine. Right? Then only I will be able to count. I will be able to do the sum. So between the map reduce, there is a step that this is map, this is reduce. There is a step called shuffle. What it do is, let's say ABC. ABC has every string have a hash value. Like if I say ABC, so I can say this is like if I translate it to numbers, so it could be, let's say, 3 or 32. Okay, and now since I had to decide between three machines where this ABC key should go, so I can simply say modulus of 3. Like basically I will divide it by 3, and whatever the remainder is, it's a 2. So if I take the modulus, so it will give me a range of 0, 1, 2 in this range, right? When this modulus operator gives me the remainder after the division. So the remainder could be either 0, 1 and 2. So based on this, I can assign my key to a particular machine. So for ABC, it will go on second machine. For CDH, let's say it is 31, and it is assigned on first machine. Okay. So all the records which are with the key of CDH will be transferred to this first machine, and all the records which are having ABC will be transferred to second machine. Now after this part is done, I will be having the distribution where all the records which carry ABC will be in same machine, right? The purpose of the shuffle is to make the records in a same machine, like wherever we perform to uh, on whichever key we want to perform the aggregation. The shuffle help us to place all the relevant keys in the same machine, so that we can easily perform the reduce operation. Because if I am having an array 2, 3, 5, 6, I cannot sum it up if these two records are present in another machine and these two records present in another machine. They need to be in same machine to be aggregated. So once this step is done, then reduce phase will reduce them. It will perform the sum, and then we will get the output. This is what the concept of map reduce. Like how a particular system works in a distributed fashion. You, I know you had a lot of questions. Please ask. Like I will tell you like what the motto of this like why I'm telling you the all the concept of this Hadoop and distributed file system and distributed compute. Basically, in the next section, next sessions, we will be discussing about Apache Spark. We will be talking about Hive. So when we are talking about big data, we never store anything, and we never run any compute on a single machine because the volumes are huge. Otherwise, we cannot even term it as big data, right? The whole point of data engineering is uh, we had to run things in a scalable manner. When we talk of a scale, we talk in terms of cluster. We talk in terms of multiple machines, not in terms of single machine. And we don't have to be too overwhelmed with the concept of this map reduce, okay, or even the distributed file system. It is totally abstracted from us. Basically, if I tell you, when you had to store something in HDFS, let's say you had some file available on your local system, let's say some abcd.txt, okay, and I wanted to put it into HDFS. Then I don't have to write big codes or something. They provide a very easy API where I can simply type like uh, HDFS 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 hyphen hyphen F, where I will be like copy from local, and I will provide the my current path text like abcd.txt, and I will provide my HDFS path like I want to store this file in the folder like data temp abcd or abcd.txt. So it's simple as that. We don't have to write big codes. I just want I'm just trying to explain the internal things so that you uh, when the interviewer will ask you about the things, then you will not be left blank. You will have answers to the questions. You will have the overall understanding of the system architecture, like how the things work. When I'm talking for the distributed compute, okay, we would be using Spark. Almost everything will be abstracted, and we will be writing SQL queries. We will be writing things in a SQL style, which we did in SQL sessions. But that will be running in a distributed way. So if we know the underlying, like how exactly the queries are running within, then we will have a better edge over other people, because we will be able to think from very from more holistic view, and able to even debug the difficult issues. Okay, so this is about the distributed file system and distributed compute. We will talk about Hive. We will talk about how to do local installation for the Hive, and how to run local Spark locally um, in the next session, and how we will write a small code to do the data transformations. We will read the data, transform it, write it into some tables. We will query those tables. Uh, all those things we will do in the coming session. So, for today, are you clear with the map reduce and the okay? So, got it. Like by reduce, Reduce means you can broadly you can categorize reduce means aggregation. Okay, so whenever we are doing aggregation, we are reducing. Okay, now aggregation could be anything. Like let's talk in terms of SQL. Okay, SQL now we all understand. So I talked of this small SQL, or let's say we talked about any other SQL. Um, we wanted to get the average price for the, like what, how, how much is the average cost for a single person if we go to the certain restaurant. Hmm? So we need to fetch the average price of all the items a particular restaurant have. Hmm? Now to perform that average, hmm? to perform that average, let me just talk in terms of little bit in terms of code, then you will understand it better. So I had, let me talk in terms of key value pair. So this is my restaurant ID, one, okay, and I the value is 20, 130, 250, again 120, something like this. Okay. Now if I say these two records are in my machine 1 and those two records are in my machine 2, okay, will I be able to perform the average? Like to perform an average on a basic array, I have an array 1, 2, 3, 4, 5, and I wanted to perform an average on it. Then my simple code would be add all the elements divided by the length of it. Correct? But if I try to apply the same thing, add all the elements wherever I found one, okay, and take the average here and here, it doesn't help because the net average would be for the first for the restaurant with the ID 1 would be like 20, 20, 30, whatever the average number will be, 25. Hmm. So that should be my average. So the to perform that aggregation, I need to bring all the records of the since I am performing the aggregation on the first key on my restaurant ID. I need to put all the records of that relevant restaurant ID on a single machine. Then only I will be able to perform this operation, right? Then it's my operation is simple. Got it till here? Right. Yep. It's like in between map and reduce, like before reduce there exists a shuffle. So what this shuffle do is, since we cannot communicate, like the one is here. So how the shuffle works, so this one is, let's say I have two machines, so 1 modulus by 2, I'm dividing and taking the remainder. Okay, so it is going to one machine, and the second record with the ID 2, if I take the remainder and divide it by 2, it is 0. Hmm. So that means if I send all the records of 1 to the first machine and all the records with 2 on the 0th machine, like you can call it as machine 1, machine 2, okay, then my problem is solved. So it do shuffle based on the hashing, okay, and the resultant set would be something like this: 120, 130, and 120. Now they are in same machine, and this 250 are in another machine. Now this same operation is performed like in the reduce. So this is how the aggregation works in distributed way. All right. So any more questions around these two concepts? We will talk more about it when we were learning Spark and we will be writing code. Right. As I told you, like everything is abstracted. By abstraction, I mean you had frameworks, you had libraries, you had tools which do all the work internally. You just had to write plain SQL queries. You had to write small codes. We will learn how to write those codes. Um, but it is I think it is important to know how things are working internally to get a very to get a bigger picture understanding. Okay, then like if there is no question, then we can conclude the class. Then we can meet tomorrow with our Hive and Spark setup ready, and can continue from there. Mm-hmm. Mm-hmm. Okay. Sure, sure. I will send out few videos. Okay, you can follow that. Then in the session itself, if you had any issues, you can post in the group as well. And in the session, I will again like reconcile with all of you that if you guys are able to do that, or I can do it live directly that time. Okay. All right then.